Hi, in this video we are going to look at linear discriminant analysis, or sometimes known as LDA. So here we will look at LDA, but you may also have seen something called PCA. What is the difference between PCA and LDA? There are two words, isn't it? Principal component analysis. In this case, PCA is actually stand for principal component analysis. Here it deals with unlabeled data, and it tries to maximize variance. Okay, that is PCA. So LDA, in contrast to that, deals with labeled data. That means we can have class 1, class 2, class 3, so on and so forth. These are labeled with different classes, and it tries to maximize the discrimination between the classes. So unlabeled data and tries to maximize the variance. The variance is PCA. Labeled data, which tries to maximize the discrimination or the separation between the classes, and that is the separation between the means, as well as is try to minimize the variance. So we'll see there are two things actually it looks at. In the case of LDA, it actually try to maximize the separation between the classes, as well as the try to minimize the variance. So in fact, if I write an equation for this one, for maximize, you find a direction in which maximize a Jacobian with mean separation between the two means to be maximized, as well as the minimize the scatter. This is sometimes called scatter or the variance. We will come to this one in a minute, what these things are. So in fact, this is the generic equation. Sometimes we call this one is the Fisher LDA. This is called the Fisher discriminant. Fisher linear discriminant objectives. Okay, this is our target now. So we are trying to find out a vector W in which, if you project the data onto this vector, we get the maximum discrimination between the two classes. So let's see what this means. At the moment, you may look it a bit difficult to understand. So to go about this question of understanding this one, we'll try to get a. So basically, we normally know what is the data matrix is. Data matrix is normally consists of attributes, A1, A2 attributes. You have your instances x1, x2 up to xn. So each attribute have values x1, 2, x2, 1, x2n, xn1, xn1. Similarly, attribute 2, x2, 1, x2, 2, and xn2. So this is our usual data matrix in which we don't have any classes. But for this particular problem, because we are looking at maximizing the separation between two classes, let's take two different matrices. One is for data matrix 1. So we have a data of class 1. So we will take some values for the class 1 data. Let's assume these values to be, let's take some values that I have 4, 6, 1, 2, 1, 4, 2, 2, 2, 3. And for data 2, we take another matrix, which is second data matrix, so which is 3, 1, 4, 1, 4, 2, 5, 2, 5, 4. So let's try to visualize what these data are. So let's try to plot them in this graph here. So let's try to have x-axis is our, these are basically attribute 1 and attribute 2, attribute 1, attribute 2, and the instances are going like this: x1 up to xn, x1 up to xn for the two data matrices. So basically we have a1 and we have attribute a2. So if you plot these points here, 5, 10, first point is 4, 6, in this case 5, and 4, 6, first point is 4, 6 here, 1, 2 here, 1, 4, 1, 2, 1, 4, 1, 4 here, 2, 2 here, 2, 3. This is our data class 1. So data class 2, we have 3, 1, 4, 1, 4, 2, 5, 2, 5, 4. So these are the two classes. This is 5, this is 5 here. So it looks like this, if you try to classify this one using A1, if you project them into this axis, you see that there will be a overlap of data. Also, if you try to project it into y-axis, you can see there will be an overlap of data because you cannot find a proper separation. In fact, what will be the best axis to project these two classes? Therefore, we can get an unoverlapped two classes, or at least less overlapped. That means we have to maximize the separation between the two means, and then minimize the scatter. Scatter minimize means that if you say that we have some points 1, 2, 3, 4 points here, so if you want to project it into this is your scatter. But if you project this into a line like this, so depending on the line that you have selected, so this is your scatter. But if you had selected this line, if you project it to this line, so your scatter will be less. The amount of scatter, depending your projected vector, you can reduce the scatter. So here also we may look something like this. Say if you project it into this direction, say if I take a direction like this, it may probably give a better understanding. That means you project this line, this point into this line, you get a less scatter. And so in fact we will get a line very close to that that vector. Let's see how we are going to find out this w direction. So this w direction, this w vector can be calculated by a simple equation. Again, I'm not going to show you how this equation is obtained. We can show that in another video, but for the moment I am going to use it as it is. That means this is a very important equation. S minus 1 b times w is equal to alpha times w. So alpha are the eigenvalues. This eigenvalue problem, eigenvalues of this matrix. This matrix is interesting. Here S means scatter matrix and B means between class scatter matrix. We'll come to this one again. I'll explain what this means. So that means if you have this condition, that means if you find eigenvalues for this matrix, if you find eigenvalues for this matrix, say lambda 1, lambda 2, the dominant eigenvalue, say lambda 1 is greater than lambda 2 or if you have in this case you get only 2 lambdas because two class problem, two attributes. So we have lambda 1, say lambda 1 is greater than lambda 2, that is means lambda 1 is the dominant eigenvalue. So that dominant eigenvalue will produce this W. So using that dominant eigenvalue, you can obtain the direction at which you can get the maximum separation between the two classes, as well as the minimum variance, minimum scatter. Actually, we call it minimum scatter. Actually, you can write an equation for scatter. S squared is equal to n times variance. This is another equation. So it's the total scatter is the total square deviation from the mean, but variance is the average deviation from the mean. So it is quite interchangeably used. Let's try to use this numerical problem to iron out our thought process. So first of all, let's try to find out our D1. So we have D1. D1 is equal to 4, 6, 1, 2, 1, 4, 2, 2, 2, 3. So in our process, what we are going to find out, we are after scatter matrix, and we are after B, the between class scatter matrix. So to do that one, we'll take the two matrices. We have D1, and we need to find out. Yeah, anyway, let's write the D2 also. D2 is the other data matrix that we have. D2 is equal to 3, 1, 4, 1, 4, 2, 5, 2, 5, 4. And what is our mu1 for the first data matrix? So basically what we can do is we can calculate the mu1 by summation of the first row, 4 plus 1 plus 1 plus 2 plus 2. In fact, this data matrix 1 will have two mu values, that is for attribute 1, attribute 2. Similarly, we get for attribute 1 and attribute 2, there will be two mu values. Therefore, we have two elements in this matrix, and 1 over 5 sigma 6, 2, 4, 2 plus 3, 6 plus 2 plus 4 plus 2 plus 3. These are the two elements in this mean vector. So mean vector, when you simplify, you get 2, 3.4 for this mu1. Similarly, mu2, we can do the same process, 1 over 5 sigma 3 plus 4 plus 4 plus 5 plus 5, and then second element 1 over 5 1 plus 1 plus 2 plus 2 plus 4. So if you simplify this, we get 4.2 and 2. That is our mu1 is equal to 3.4, mu2 is equal to 4.2 and 2. Now we have a definition for scatter matrix, which is called S1. That is for the scatter matrix for D1 is known as S1, which is equal to sigma xi in D1 xi minus mu1 times xi minus mu1. So we are still finding the scatter matrix for D1 transpose. So it looks quite familiar to you if you have seen my previous video. This is like you are centering the data by taking away mu from all the points. That means if you take away average from all the points, you will center the data. So similar argument can be applied here to find out xi minus mu1 by actually using a data matrix, or we can simply in here to make it more simple, what I'm going to do is I'm going to do it in a long way. So if you are familiar with that matrix notation, how to center, actually you can try this method. Z is equal to D1 minus 1 vector, all one vector times mu1 transpose. this is how you can do this question, some simplification to get the scatter matrix D1, which is equal to the first part of this. This is it here, and then you can actually calculate the rest and then multiply. But yeah, so in here you have seen that if you can remember, if you can look at the video, it's actually we can take away this one from D1, 4 6 1 2 1 4 2 2 2 3, and then minus, actually this is all one vector multiplied with mu1 transpose, that is 2 3.4 when you take transpose. So we can actually get 4 6 1 2 1 4 2 2 2 3 minus all these values will be negated 3.4. Sorry, this is our 2 3.4 2 3.4. It repeats. Actually, when you multiply this case, you get all like this: 2 3.4 2 3.4. So when you simplify, you get the Z matrix. So it's again you can do that way, but I prefer you can do it in a much simpler way without going into complex mathematics, if you prefer that way. So okay, let's try to do it in a simple way. That is, if I want to calculate x1 mu1, which is equal to our x1 vector. X1 vector is our, yeah, so we have vectors. X1 is 4 6. Yeah, if you look back here, this is our 4 6. X2 is 1 2. Each of the rows in this we'll look at as vectors here. X2 1 4, and X4 is 2 2 2 2. X5 is 2 3. This is our vectors, all the points. And if you take away mu1 from all the vectors, 4 6 minus mu1, our mu1 vector, we found it to be equal to 2 3.4 2 3.4. So when you take away this one, you get 2 minus 2.6. Sorry, 2 plus 2.6. Sorry, it's plus 2.6. Okay. So similarly, we can calculate for the other x2 minus mu1, which is equal to 1 2 minus 2 3.4. We get minus 1 minus 1.4. X3 minus mu2, which is equal to 1 4 minus 2 3.4. Always we are taking away mu1. This is for the centering of the data set 1. We have only one mu, that is mu1. So we take these values is minus 1.6, and x4 minus mu1 is equal to 2 2 minus 2 3.4, which is equal to 0 minus 1.4. x5 minus mu1 is equal to 2 3 minus 2 3.4, which is equal to 0 minus 0.4. Okay, so this is our first data set, which we actually need to find out for scatter. We need to find out sigma xi in D1, which is xi minus mu1 times xi minus mu1 transpose. So we have all the values. Now what we need to do is we need to multiply and then do the addition. 2.6, this is the first vector, x1 mu1, and then transpose to 2.6 plus x2 mu1 minus 1 minus 1.4 plus x3 minus 1.6 times minus 1.6. So on and so forth. You can go up to 5 points. We have 5 points. x4 is 0 minus 1.4, 0 minus 1.4, plus the last point is 0 minus 0.4 times 0 minus 0 minus 0.4. Excellent. So once we do this simplification, I hope you will be able to do that. That means once you multiply this guy, we get 4 5.2 5.2 6.76. So please try to see, then plus when you multiply 1, 1.4, 1.4, 1.96 plus 1 minus 0.6 minus 0.6, 0.36 6 plus 0, 0, 0. This is interesting. So we have, give me a second, here. So 0, 0 minus 0.4. So 0, 0. So in this case 0, 0, 1.96 and plus last one 0, 0, 0, 0.16. So when you add all this, we get our scatter matrix for data matrix D1. Okay, so interesting. So it's quite straightforward. So we calculated each element and take away its mean and then got the value, and then we multiply by its own transpose. This is our definition for scatter matrix. So transpose xi minus mu1 transpose. So we got the scatter matrix for S1. So this is S1. Similarly, we can find S2, which is the scatter matrix for D2. Yes, if you calculate that value, you can find S2 is 2.8336. That is for matrix 2. So we can find S. S is equal to S1 plus S2. Just add this to S1, S2. So you have 66611.2 plus 2.8336. So when you add, you get the scatter matrix for this question. So S is equal to 8.89917.6. Okay, cool. So now we need to find the other matrix, which is, so there is something that we need to do. We need to find the S minus 1. Let's do that one also. S minus 1 is equal to inverse of S, which actually we find the modulus of this one. Basically 8.8 times 17.6 minus 81 is the modulus of this matrix. Divide by, so you swap this 17.6 here, come 8.8 comes there, this will become negative, it's a negative 9. So this whole thing will be our S minus 1 in inverse of this matrix. So this is equal to, you simplify, 70.36. So when you, if you calculate the value for the inverse, 0.244 minus 0.128 minus 0.128, 0.125. That is our S minus inverse of the scatter matrix. Now we want to find out B, which is called the between class scatter matrix. It is defined by very simple equation here, which is equal to mu1 minus mu2 vector form multiplied by mu1 minus mu2 vector form transpose. So it's quite straightforward, very easy to calculate this one, because we have only 2 by 2 matrix, which 2, 3.4 minus 4.22, so which is mu1. So let's try to do this one first. Mu2, which is equal to minus 2.2, 1.4. Okay, so therefore B is equal to minus 2.2, 1.4 multiplied by minus 2.2, 1.4. This is the transpose of the mu1 minus mu2. So when you multiply this one, you get the scatter matrix 4.84 minus 3.08 minus 3.08, 1.96. Interesting. So we have these two vectors, these two matrices. Now we want to find out, sorry, inverse, did I minus 1, so it's minus 1 normally. So we want to find the inverse of the matrix S minus 1. So s minus 1 times b is now we are after. So s minus 1 we found 0.244 minus 0.128 minus 0.128 0.125 multiplied by b 4.84 minus 3.08 minus 3.08 1.96, which will give us 1.575 minus 1.002 minus 1.005 0.639. Okay, so now we are off to the final answer. So what we now looking at is s minus 1 bw is equal to alpha times w. So this is an eigenvalue problem in which w is the eigenvector. So if you find the eigenvalues of this s minus 1b, we will get the solution. Let's try to find the eigenvalues of s minus 1b. So how to find eigenvalues? So we'll use the very classical technique, 1.57 minus lambda minus 1.022 minus 1.005 0.639 minus lambda modulus is equal to 0. It is actually, we just we have the matrix minus I lambda matrix. Basically we have the original matrix s minus 1 b, so we minus I times lambda and the modulus equal to 0. So this is our eigenvalue problem. Okay, so we can find the determinant of this here. So if you calculate 1.575 minus lambda times 0.639 minus lambda minus, actually this is minus 1.002 times minus 1.005 equal to 0. So this will become positive, there will be a negative sign in any way. So now we are getting there. So we have the eigenvector, sorry, the equation to find the eigenvalue. So please try to simplify this guy here. So you get maybe 1.006 minus 1.575 lambda minus 0.639 lambda squared plus, sorry, 639 lambda plus lambda squared minus 1.007 equal to 0. So we get lambda squared minus 2.214 lambda minus 0.001 equal to 0. So we can, this is quadratic equation. We have two lambdas. Lambda 1 is equal to 2. So it's basically, you know what to do. Lambda is equal to minus b plus or minus square root of b squared minus 4ac over 2a. So in this case b is minus b 2.214 plus or minus, sorry, if I take the positive value for lambda 1, so I take plus here square root of b squared 2.214 squared minus 4ac. So c is negative, so you get 2001 become positive, divide by 2. So when you simplify this guy, you will get a value for lambda 1 2.2155. Similarly, you can find lambda 2, which is 2.214 minus square root of 2.214 squared plus 0.01 divided by 2, which will be, actually if you calculate, it will become 0. So actually we have a very dominant lambda, which is the dominant eigenvalue. So we can use that dominant eigenvalue to find out our linear discriminant direction. So the maximum discriminant will be given by w. So basically you use the mu1 and then lambda 1, you substitute into the same equation that we found lambda. So it is minus 2.2155 minus 1.002 minus 1.005 0.639 minus 2.2155. xy is the vector that we are after, which will be equal to 0 0. In this particular case, what we are doing is to the simplification and find out the relation between x and y, which will give us minus 0.64x minus 1 point. Even if you do the row 1 or row 2, you should get the same relation between x and y. So if you write simplified, x and y will have relation minus 1.5661, which actually, or if you want one more step, I will show this other step. That will be better to show how we got this one. Basically what I do here is xy is equal to minus 1.002 divided by minus 0.64. In this case it will be plus, because when you move it to the other side, one become plus and then the other one will become 1. So this is because 1.102 we divide by the quotient of x. So when you cross multiply, you get the same value. So you get minus 1.5661, which is not a unit vector. So what we now do is to find out the unit vector. That means to find out w, which is the maximum linear discriminant direction, so which will be given by 1.566 squared plus 1 and then minus 1.5661, which is a linear unit vector. So unit vector will be, when you calculate w, can be found to be equal to minus 0.843, 0.538. Wow, that is our linear discriminant direction. So the largest eigenvalue of S1, largest eigenvalue of S minus 1b will give the best linear discriminant direction vector actually, or direction. So it's a direction, so it's not a like a line, but it's only a direction that we get. So what, yeah, so if you want to go back and plot this one in our graph that we got, let's see what's going to happen. So this is our answer. So this is the linear discriminant direction. That is, if you have two data sets, we had data d1 and d2, we had some numerical values, we used s minus 1b, calculated s minus 1b, the scatter matrix in inverse scatter matrix times the between class scatter matrix, and then we found the eigenvalue of that vector, that matrix, that simply the direction of the linear discriminant. So let's try to plot this guy on our graph what we drew earlier. So let's see where we stand there. So are we going to get it correctly? Let's see. Okay, here this is our direction. Let me select a different color. Okay, so let's try to see what we got just now. We got w is our linear discriminant direction, which is equal to minus 0.843, 0.538. So our data are here. So we have two data sets, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So what this direction means, so we can choose any random point, say this point. I just want to say, let's erase this line here and then try to make it a bit cleaner here. Okay, so this is our original data matrix. So data actually plot. Let's take for completeness, let's take our mu1. Let's take we want to plot this through our mu, which is mu. Let's take mu1 plus mu2. This is our total mean of the both data sets. So we have mu1 for data set 1, mu2 for data set 2. Let's take the mu1 and mu2 is a addition of that. That means we have mu1 equal to what we got was 3.4, and then this one, and then divide by 2 to average it. So 4.2 and 2, and then half. Bit awkward here. So anyway, so what you got, what we will get here is that the 4.2 plus 6.2, 3.1, and 5.6, 2.8. So this is our mean of the the total data set 1 and data set 2. So we have a point 3.1 to 0.8 somewhere here. Anyway, so this is the point that what I'm going to do is I'm going to plot our vector minus 0.843 and 0.58 in this point here. So minus point, that means x you get going to negative side, minus 0.8 is quite tedious anyway. So this one is 1, so it is 0.8 go that way, 0.5 go upwards. So this is our vector. Now we can plot the linear discriminant direction in which goes through mean, and then like that. So it looks approximately like that. Okay, so once we have this plot, it's a matter of looking at the projection. So what are the projections? So if you project these points onto this line, we can see it's the minimum. So basically the variance is quite minimum, as well as the separation between two classes. So they are not overlapping now, because this direction will give us a clear boundary. Anyways, there can be overlap depending on your data set, but what we found in this case is when we found the linear discriminant direction, it gave us the best line that can separate our mu1 and mu2, the two means of the mu1 and mu2, as well as the variance of these points. That means if the projected variance onto this line is minimized. So that means data are crunched. So basically you can get a better picture of the two classes when you do the classification. Okay, so that's quite interesting. So all things boiled out to this simple matrix. So if you can find S minus 1b of any two data sets, any number of data sets. So in this case we only use two data sets, D1 and D2, and then we find the eigenvalues, and these eigenvalues will produce us our W, that is the eigenvalues, but we use the dominant eigenvalue. Dominant eigenvalue will give us the direction in which that will have the best discrimination between the two classes. Okay, thank you very much.